Hi, so today I'm reading prediction with model misspecification and agnostic distribution shift. This one is from Kwang, Xiang, Sui, Ethni, Li from Zhejiang, Tsinghua, Stanford University. Abstract is, for many machine learning algorithms, two main assumptions are required to guarantee performance. One is that the test data are drawn from the same distribution as the training data, and the other is that the model is correctly specified. In real applications, however, we often have little prior knowledge on the test data and on the underlying true model. Under model misspecification, agnostic distribution shift between the training and test data leads to inaccuracy of the parameter estimation and instability of prediction across unknown test data. To address these problems, we propose novel decorrelated weighting regression algorithm, which gently optimizes variable decorrelation, regularizer, and weighted regression model. The variable decorrelation regularizer estimates the weight for each sample such that variables are decorrelated on the weighted training data. Then these weights are used in the weighting regression to improve the accuracy of estimation on the effect of each variable, thus help to improve the stability of prediction across unknown test data. Extensive experiments clearly demonstrate that our DWR, distributed weighted regression, algorithm can significantly improve accuracy of the parameter estimation and stability of the prediction with a model misspecification and agnostic distribution shift. Okay, interaction. Predicting unknown outcomes based on the model estimated on the training data set in common machine learning problems. Many machine learning algorithms have been proposed and shown that to be very successful for prediction when the test data have the same distribution as the training data on the model specification or the model specification is correct. In real applications, however, we rarely know underlying true model for prediction, and we cannot guarantee the unknown test data will have the same distribution as the training data. For example, different geographies, schools, or hospitals may draw from different demographics, and the correlation structure among demographics may also vary. For example, one ethnic group more or less disadvantaged in different geographies. If the model is misspecified, it may exploit subclassical relationship between the features present in the training data to improve prediction, resulting in inaccuracy of the parameter estimation, instability of the prediction across the test data sets with different distributions. To correct the distribution shift between training and the test data, many methods have been proposed in the domain adaptation 2009 and transfer-learning 2009. The motivation of these methods is to adjust the distribution of the training data to mimic the distribution of the test data, so that the predictive algorithm trained on the training data can minimize the predictive error on the test data. These methods achieve good performance in practice, however, they require the test data as a prior knowledge, hence they cannot be applied to address the agnostic distribution shift problem. Recently, some algorithms have been proposed to address this agnostic distribution shift from unknown test data, including domain generation, 2013 causal transfer learning, 2018, and invariant causal prediction. Their motivation is to explore invariant structures between the predictors and the response variable across the multiple training data sets for prediction, but they cannot well handle the case of distribution shifts that are not observed in training data. Moreover, they do not consider the interaction of the distribution shift and the model misspecification. Recently, some papers in 2018 were proposed to address the stable prediction problem using the methods drawn from the literature on causal inference, achieving the improved performance, but did not consider the model misspecification, and their algorithms were restricted to predictive settings with binary predictions and binary response variable. In this paper, we focus on the problem of stable prediction with the model misspecification and agnostic distribution shift, where we assume that all the features predictors X fall into one of two categories. One includes the stable features S, which have no causal effect on the outcome Y, and are invariant across environments, for example, across training and test sets. The other category includes the unstable features V, which have no causal effect on outcomes, but they may be correlated with either stable features, the outcome, or both. The correlation may be different in different environments. Under assumption that all the stable features are observed, model misspecification would be induced by some omitted nonlinear interaction terms of stable features. Since the different environments, for example, training and test sets have different coverage distribution, the parameters estimated from the different environments may be quite different, even when we use the same parametric model. This variation in parameters arises because the parameters on the included features capture two components. First, the partial effect of the included features on the effect value of the outcome, and the second, the function that depends on the correlation between the included and omitted feature, as well as distribution outcomes condition on omitted features. we consider the problem of making prediction when the second component of the estimated parameters is unstable across the environment. In that case, we prefer to find an estimator that eliminates the second component, even though it including improved prediction for the test sets that are similar to the training data. We look for an algorithm that is effective when the analyst does not know which feature is stable and which is not. One way to address this problem of stable prediction in such setting is to isolate the impact of each individual feature. One commonly used in the causal literature is covariate balancing 2018-17, which essentially estimates the impact of target variable by deriving the data such that the distribution of covariates is equalized across the different values of the target feature. This literature usually focuses on the case where there is a single pre-specified feature of interest and other features are considered to be confounders. In this paper, we considered a case where there are potentially many stable features and propose novel decorrelated weighting regression algorithm for stable prediction with model misspecification and agnostic distribution should by gently optimizing variable decorrelation regularizer and weighted regression model. Specifically, the variable decorrelation regularizer controls sample weights to reduce correlation among variables and allows the weighted regression to approximately isolate the effect of each variable. The weighted regression model with those samples weights might perform worse than the standard methods when predicting the test data with similar distribution to the training, but it will do better across unknown test data with distribution shift from the training. Using both experiments and theoretical analysis, we showed that our algorithm outperforms alternatives in parameter estimation and stability in prediction across unknown test data. This paper has three main contributions. 1. We investigate the problem of stable prediction with model misspecification and agnostic distribution shift. The problem setting is more general and practical than prior work. 2. We propose a novel DWR algorithm to jointly optimize variable decorrelation and weighted regression to address the stable prediction problem. 3. We conduct extensive experiments in both synthetic and real-world data sets to demonstrate the advantages of our algorithm on stable prediction problem. Problem and our algorithm. In this section, we give a formulation of the stable prediction problem and then introduce the details of our algorithm. Stable prediction problem. Let X denote the space of observed features and Y denote the outcome space. We define an environment to be joint distribution P of X and Y on space X cross Y and let epsilon denote the set of all environments. In each environment, in big epsilon, we have dataset D equals X and Y, where X is in space X and predictor variables Y are in Y space is a response variable. The joint distribution of the features and outcomes on X and Y can change across the environments. In this paper, our goal is to run predictive model for stable prediction with model misspecification and agnostic distribution shift to measure its performance on the stable prediction problem without average error and stability error as found. Our epsilon refers to the number of test environments and root mean square error represent root mean square error of predictive model on dataset D. Actually, average error and stability error refers to means and variance of the predictive error over environments. Then stable prediction problem is defined as stable prediction. Given one training environment with data set, the task is to learn predictive model to predict across unknown environments epsilon with not only small average error but also small stability error. Okay, let me backtrack a little bit to see what is the stability error once more. So the average error, that seems to be the classic, average over root mean square error, and the stability error here is a sort of root mean squared error minus. So how far is the root mean square error sort of from the average error? It seems to, yes, so stability error refers to the mean and variance of the predictive error over all possible environment. Okay, so stability error is variance of predictive error over over the all possible environments. So it's sort of like a difference, how far is this root mean square error from average in terms of the variance. So, and the stable prediction is that given one training environment, task is to learn predictive model to predict across unknown environment with not only small average error but also small stability error. So they want to have small average error, but also they want to have small this variance of the error. They also want to have that one small. And then they have this assumption: there exists a function f such that for all environments equals f. So what are they saying? Assumption 1 can be guaranteed by thus we can address the stable prediction by developing a predicted model that learns the stable function, but we have no prior knowledge on which features are stable and which are unstable. So we make another assumption that all stable features are observed. Under assumption 2, model misspecification will be induced when estimating an outcome function if the model omits some nonlinear transformation and interaction terms of the stable features. Suppose that we have a true stable function f and y in an environment by where we assume that the analyst misspecifies the model omitting g and uses linear model prediction. Under assumption 1, the distribution shift across the environments is mainly induced by the variance in the joint distribution over v and s. Simple linear regression may estimate non-zero effects of unstable features when v is correlated with omitted variables. V is a resonant bias. Okay, I'm gonna go forward a little bit. I don't want to, get stuck on the details. Although those may be actually the core, but I think I won't be able to explain them efficiently here. Variable decorrelation. In this subsection, we introduce our variable decorrelation regularizer to reduce the correlation between V and S or GS. Once more, V and S are where we have that. Stable features. So S are stable features and V are unstable features, right? So in this subsection, we introduce our variable decorrelation regularizer to reduce correlation between the stable and unstable features in the training environment. Fix is mutually independent means 0. Then okay. Then we have a lemma proof here. What is the lemma? If the number of coverage p is fixed, then there exists sample weights such that limit of this loss, I guess, it's a 0 with probability 1. In particular, the solution to W equation 9 is these specific weights. Oh, damn it, I clicked on something. Kernel doesn't estimators. See appendix. Okay. Following theoretical results proved in the supplementary material show that our variable decorrelation regularizer can make the variables in X become mutually uncorrelated by sample reweighting. Hence, reduce the correlation among the covariates in the training environment and improve the accuracy of the parameter estimation. Theorem 1. The solution W described in equation 10 is unique if then we have these. Property 1. P is fixed and Sn goes to infinity and Wn is bigger than something, P square is bigger than something. The variables in X become uncorrelated by sample reweighting with W. Hence the correlation between the V and S in the training environment will become reduced. Extensive empirical experiments demonstrate the correlation between stable and projection of or map of the unstable features and projection of the stable feature will also become reduced by our regularizer. In summary, we propose variable decorrelation regularizer in equation 10 that can learn unique optimal sample weights that can decorrelate the variables X and thus improve accuracy in perimeter estimation and stability in prediction. Decorrelated weighted regression. Weighted regression. Optimization analysis. To optimize DWR algorithm in equation 12, we propose an iterative method. First, we initialize sample weights for each sample E regression coefficient. Once initial values are given, each iteration first update W by fixing beta and then update beta by fixing W until the objective function in equation 12 converges. The whole algorithm is summarized in algorithm 1. So algorithm 1, decorrelated weighted regression algorithm. Require opposite feature x and outcome variable y. Ensure updated parameters w and beta. So initialize parameters w and beta. Calculate loss functions with loss function with parameters w and beta. Initialize iterable iteration variable t. Repeat. Do t plus 1. Update w with gradient descent by fixing beta. Update beta with gradient descent by fixing w. Calculate loss function with parameters w and beta until loss function converges of max iteration is reached. Return w and beta. Complexity analysis. In our DWR algorithm's main time cost is calculate value of loss function and update parameters w and beta in each iteration. The complexity of calculating the loss function is complexity n times p squared, when n is the sample size and p refers to dimension of observed variables. The complexity of the updating parameter w is also complexity n times p squared. The complexity of updating parameter is numbers sample size n times p the dimension. In total, complexity of each iteration algorithm 1 is number of samples times dimensionality squared. Experiments. In this section, we check the performance of our algorithm with experience in both synthetic and regular datasets. We use following four methods as the baselines: Ontario least squared, lasso, ridge regression. Okay. Figure 1, figure 2. Okay, I'm not gonna be looking at those right now. Independent interpretable lasso, avoid degeneration, evaluation metrics. To evaluate performance of the stable prediction, we use root mean squared error, beta error, average error, stability error as an evaluation metrics. Their definitions are following. Beta error. Okay, so experiment on synthetic data. Dataset under assumption 1, there are three kinds of relationship between x stable features and unstable features, and w as shown in figure 1, including the stable features might be orthogonal to unstable features. Stable features might sort of imply or cause unstable features, and unstable features might imply stable features. We consider setting motivated by each of the three cases as follows. So stable features orthogonal. In this setting, the says are independent. No, they mean not orthogonal, they mean independent, but S could be dependent with each other. Hence, we generate these variables with independent Gaussian distribution with help of auxiliary variables as following. Okay, they use these Gaussians. Okay, and then we have this other case where S arrow points to V. In this setting, the stable features are causes of unstable features V. We first generate differentiable features and then generate unstable features. Okay, right? I think I get it. Generating various experiments to test the stability of our example. We generate a set of experiments for each distinct distribution while serving assumption 1. Specifically, we generate different events in our experiments, varying EP for simplification, experimental setting. Okay, results. Before reporting experimental results, we demonstrated Pearson correlation coefficients between any two variables on both raw data and weighted by algorithm in figure 2. From figures, we can find that the raw data and stable features correlated with some of the stable features and higher correlated with both omitted linear term G and outcome W. Hence, the estimate coefficient V5 in the baseline would be large, which should be 0 in the correctly specified model. Okay, so from the results we have following observation and analysis. This is OLS once more. What is the ordinary least squares, of course. Okay, ordinary least squares cannot address the stable prediction problem. The reason is that ordinary least squares is biased in both PS and BV estimation as discussed in the theoretical section. Moreover, ordinary least squares will often predict large effects for unstable features which lead to instability across environments. Lasso and Ridge also performed even worse than OLS since their regularizers will generally estimate relative coefficients on unstable features. For example, Lasso affects only a subset of prediction and exacerbates the omitted variables problem that already exists in our basic setup. Comparing with the baselines, our algorithm achieves more stable prediction across different settings. By reducing the correlation among the old predictors, our algorithm avoids using unstable features to proxy for omitted nonlinear functions on stable features, ensuring less bias in the estimation of the effect on both stable features and unstable features, hence improved stability of the prediction. By varying sample size, dimension, consistently outperform, overall DWR algorithms can be applied to address problem of stable prediction with model misspecification and agnostic distribution shift. Okay, we have more results. On real-world data, we report that the RMSE, root mean square error on air quality predicted over all 10 states, emerge least squared error, ordinary least squares error, least squares method into Lasso by allowing hyperparameter. The results show that the performance of our algorithm is worse than baselines when the distribution distance between training and test diagram is small. In that case, we introduce variance by reweighting the data away from the distribution that approximates both training and test set. But our algorithm's performance improves relative to baseline and ultimately becomes better than baseline as the distribution distance increases. To explicitly demonstrate conclusion. In this paper, we focus on how to facilitate stable prediction across unknown test data, where we are concerned about two problems that together lead to instability. Model misspecification and agnostic distribution shift between the training and test data. We prove that our algorithms can improve the accuracy of parameter estimation and stability prediction from both theoretical analysis and empirical experiments. The experimental results on both synthetic and real-world dataset demonstrate that our algorithm outperforms the baseline for stable prediction across the unknown test and environments, and the correlating among variables vary substantially across environments. Okay, that would be all. Thank you very much. If you have any suggestions how to improve this, podcast, please let me know. And under no circumstance, subscribe and never like these videos. Please, thank you very much. Okay, see you next time. Bye.